Series, or infinite sums, are linear. This refers to these two properties. If I have a series whose general term is the sum of two separate terms, then I can split it at the sum of two series. And if I have a series whose general term is a constant times something else, then I can take the constant out. Looking at these two properties, perhaps your reaction is, well, that's obviously true. Do we have to waste any time on this? Do we have to bother proving it? Yes, to justify why these properties are not obvious and we cannot take them for granted, I want to first look at a different property that surprisingly happens to be false. I'm going to do that with an example. Let's look at this infinite sum. It's 1 minus a half plus a third minus a quarter and so on. So it's the sum of the reciprocal of all the positive integers, but the odd ones I add and the even ones I subtract. This infinite sum happens to be convergent and the value is logarithm of 2. This is non-obvious at all, and I'm not going to prove it now. For now, just trust me on it. Now I'm going to look at the second sum, which is very similar. I'm going to take the very same terms and I'm going to reorder them. So now I add two positive ones, then one negative, then two positive, then one negative, and so on. But ultimately, in the infinite sums, it's the very same terms reordered. We would probably expect that if the first sum is convergent, so is the second and it has the same value. And indeed, the second sum is convergent, but the value of the sum is different. This should be surprising. This would make you perhaps a bit uncomfortable, and in fact, perhaps you didn't believe me. Well, I'm not going to prove it yet. Later in this series of videos, no pun intended, I will justify why this is true. I will explain it. But the reason I'm bringing it now is to explain that just because a certain property of finite sums seems intuitive and natural, and we believe it's going to be true, doesn't mean it will necessarily carry forward for infinite sums and will still be true. Finite sums can be reordered at will, but infinite sums cannot be reordered at will even when they are convergent. It may change the outcome. By contrast, linearity refers to two important properties that are true for finite sums and are still true for infinite sums. Let's have a look at them. Linearity of series is summarized by two theorems. What happens when I add two series and when I multiply a series by a constant. The first theorem says, if I begin with two series, the sum of an and the sum of bn, and I assume they're both convergent, then the combined series, the sum of an plus bn, must also be convergent, and the value of the sum is exactly what you would expect, is the sum of the other two series. So for this specific rearrangement, it works as we expected. I need to assume the two initial series are convergent, otherwise it's not true, but if they're convergent, then the rearrangement works. The second theorem is about multiplying a series by a constant. So if c is a real number, and I begin with a series, sum of an, which is convergent, then the sum of c times an is also convergent, and its value is again exactly what you would expect it to be. So this kind of property of finite sums also extends to infinite sums. But again, I need to assume that the series I begin with is convergent. As an example, I'm just going to prove the first theorem, and the proof of the second theorem works very similarly. And the proof is going to be quite straightforward. These properties, when they're true, the proof tends to be very short. We need to use the definition of infinite sum. An infinite sum is defined as a limit of finite sums. So let's do that. I say that the infinite sum of all the an's is the limit of partial sums, and I'm going to call the partial sum sk, where sk is the finite sums of the an's only up to the term k. And similarly, the other two series can be written also as limits of partial sums, but I'm going to give different names to those partial sums. So I'm going to say the sum of all the b's is the limit of the partial sum tk, where tk is a finite sum of b's, and the sum of an plus bn is the limit of the partial sum rk, where rk is the finite sums of an plus bn. And once I have written the infinite sum as a limit of finite sums, I can now manipulate the finite sums. And for finite sums, I don't have to be careful. I know that for finite sums, any of the usual manipulations is true, so I can reorder the terms. So it is true that rk equals sk plus tk. Now, the hypothesis of the theorem is that the first two series are convergent. What that means is that the first two limits exist. That's my hypothesis. So if rk equals sk plus tk, and I am assuming the first two limits exist, then simply by the limit laws, the third limit also exists and is the sum of the other two. And that's it. That completes the proof. This is kind of a template of all the common properties of series, and this is how they are all proven. First, write the infinite sum as a limit of partial sums, finite sums. Second, use the property you know is true for finite sums. And then third, pass to the limit, assuming we are allowed to pass to the limit.